welcome to this video on extracting half equations. The question we're addressing here is how can I work out reduction and oxidation processes occurring from a redox equation. So this is not constructing half equations from scratch. This is you've got a full redox equation and you want to know what are the oxidation and reduction processes occurring. There are basically two methods which we're going to go over in turn. So the first is what you're going to do if you have to suggest a second half equation for a process. So here I've got a full equation and the reduction half equation, and I'm supposed to be finding the half equation for oxidation. So in this case, the method I would suggest you use is basically a method of subtraction. But there is a little bit of care that we need to have. We can't just do the full minus the reduction. Otherwise we might end up with problems, and I'll try to show you why in a second. So the first thing we're going to do is we're going to use oxidation numbers to find out which element is reduced and oxidized in the full equation. So if I do that here, just to summarize, I can find that the hydrogen is going to get reduced and the oxygen is going to get oxidized from -2 to 0. And again, you can check my working there, and I haven't put the right numbers of each, but that's basically what's going on. So the reduction process does indeed involve hydrogen, but the point is therefore that hydrogen won't occur in the oxidation equation. Now if we do a straightforward subtraction of these, we can see that we've got two hydrogens in the full equation. We're only going to get rid of one of them by subtracting here. So what we need to do in our second step is to actually multiply the known half equations so that you have the same number of the key species present. Now what I mean by key species is simply the species which are reduced and oxidized. So these are the key species. So we want to get rid of both of those hydrogens. So we're going to multiply this reduction equation by 2. And that means every species gets multiplied by 2. So now we're pretty much ready to do the subtraction. We're going to do the full equation minus the reduction equation in order to get the oxidation half equation. So we've got 2H2O up on the top, and then we're going to have to take away 4 H pluses. We've got 4 electrons to subtract over here as well. Then we're going to come across and we've got to get rid of 2 hydrogens. They cancel, and then we're going to have O2 over here. So the final step in this is simply to rearrange so that we have only pluses, because in chemical equations we don't tend to have minus signs. So we add 4H pluses to both sides. We have 2H2O. 4H plus come over to here, the 4 electrons will come over to here as well, and we've got O2. And that's the second half equation for the oxidation process. Now here's a second situation where we're going to split a full equation, and we're asked here to to suggest possible half equations when we don't know either one of them. So this is a bit more guesswork. And the method we're going to use starts off similar, but then slightly diversifies because we haven't got anything to subtract. So we're going to need to build up from the key species. So the first thing we're going to do is use the oxidation numbers to find the key species. And if we start with, we realise that actually the sulfur goes from +2 here to actually +2.5 on average in the thiocyanate. And so we've got sulfur being oxidized. And if I then carry on with that, sulfur's being oxidized. So if I do oxidation here, I'm now on to step 2. The key species are going to go into the oxidation half equation. So that is thiosulfate and thiocyanate. And remember from the previous time, the balancing numbers should be the same as in the full equation. Now I just need to balance as necessary, so I'm going to stick in some electrons. I've got 4 minus on this side and only 2 minus on that side, so I need a couple of electrons on the left, and that's exactly what we want because oxidation is loss of electrons. and we've actually got electrons being lost here. So we're confident that this is looking good so far. Let's go back to step number 1 to find the key species from the other equation. Well, it's fairly obvious that this is going to be iodine in this case. It might not always be this obvious. That's going from 0 to -1, and so we've got a reduction process occurring here. So if we write reduction half equation, then it's going to be I2 and 2I minus, and then we just need to balance this up. We've got 2 minus on the right, 0 on the left, and so we just need 2 electrons on the left hand side. And check they add correctly. I'll leave that for you to do. If you add these together, you do indeed find the electrons cancel and we recover the equation at the top. Here I want to show you a second example of using this method where we have to split a full equation and suggest both possible half equations. There are a few pitfalls to remind you of. So the first thing is I want to try and find the key species. So first I can see here that it's the chlorine which is actually going to be reduced down to Cl minus, and then also the chlorine is actually being oxidized. Oops, wrong colour. Up to +1 in this chlorate ion. And so we've actually got a disproportionation reaction happening here. So if we start off with the oxidation half equation, we've got chlorine in there, and that's going to chlorate 1 in this case, and those are the key species. Now I just need to balance this as necessary. So I recognise here that I've got 2 chlorines on the left and 1 on the right. Now I'm just looking at my full equation and realising that actually from this 1 chlorine, 1 of the atoms is oxidised and 1 is reduced. So it actually makes a bit more sense to put a half in front of the chlorine, and then I don't double up the number of chlorates. But it doesn't matter which you do at this stage. From that I also see that I've got an oxygen on the left side, on the right side. So I need 1 on the left, and typically you supply oxygen by adding H2O. And then I'm going to add some H+ ions in order to cancel out the H2O, the hydrogens that have been added on this side. And from this I can see I've got a +1 charge on the right and nothing on the left, and so I must have an electron that I'm going to add onto here. Now that oxidation half equation should give you a little bit of trouble though, because you can see that we're going to end up with some H+ ions floating around, but there's actually only OH- here. So this is where it would be useful for you to just click the link and watch the additional video on dealing with alkaline conditions, because this is something with alkaline conditions. And broadly speaking, what we're going to do is add some OH- ions to both sides in order to cancel out the H+, and I'll show you how that works in a second. So this is going to be 2 OH- ions on both sides. Now the 2H+ and the 2 OH- here are then going to form water. So I'm going to put that there, 2H2O, and I'm going to just rewrite the rest of the equation underneath. Okay, so there we have underneath. Now you can see that we've got an H2O on the left and 2 H2Os on the right, and so we just need to cancel out the 2 from here, and we can get rid of that H2O entirely. So we end up with the oxidation half equation. If I just use my eraser, we can get rid of that, and get rid of one of those, and we get half Cl2 plus 2OH- goes to ClO minus H2O and a single electron. Now let's do reduction. Hopefully it's not going to be quite so difficult. If we have a look at the reduction, the key species in there, it's going to be Cl2, and then the other key species is going to be Cl-. So you see we don't put in the H2Os at all at this stage. Now we've got half of one of those in order to get it to balance, and then we need a single electron on the left side. And there's no complications with H+ and OH- here. And it should be possible for you to see that if you add these two together, you're going to get the electrons cancelling and we're going to get the required species on both sides. So these are the appropriate half equations for alkaline conditions. So as we summarise, two methods. First method is subtraction, and that's what you use when you've got the full equation and one half equation given. A warning there, make sure you multiply the half equation to remove the key species, making sure that you're not going to have the same species occurring in oxidation and reduction half equations if that's one of these key species that changes oxidation state. Because remember, in a half equation you can only have one element changing oxidation state. Second method is building up from the key species. If you've got the full equation given, you're doing really a bit of guesswork, and that's as good as you can do. Now in both cases, take care when you're assigning key species, so be clear on how you're going to do your oxidation numbers, and secondly, watch out for alkaline conditions and make sure you don't have any H+ ions floating around if it is alkaline.